Morning and welcome. We are Heron Innovators, home of the suspended air flotation. We are joining you today live from California, or I guess most of us are here in California. We have John Barsotti, the president, but we also are joined by Jeff Knolenberg, our vice president of sales. He is in Kentucky. I am Andrea Hofstetter, and I am so glad that you guys all took some time out today to join us for our booth, our virtual booth here at WebTech 2020. This is, our third day of doing this, and I think we've got it kind of figured out, but, there is a chat feature, and if you could use that, let us know if you're hearing any technical difficulties, any problems with the sounds, or any questions you have along the way of our presentation. We will have a questions and answer section at the very end. We'll reserve all questions for that time. But please go ahead and use that chat feature anytime. We are constantly checking it and communicating with you guys any additional information or questions you might have. For now, again, we are Heron Innovators, home of the suspended air flotation, or SAF. And I'm going to go ahead and let John introduce himself, the president of Heron Innovators.
Thank you, Andrea. Yes, I'm John Barsotti. I'm the president and founder of Heron Innovators, and I actually founded the company in 1997, and we started in someone's backyard. Now we have, well over 100 installations, and we're no longer in anybody's backyard of making these things. So I wanted to thank you for joining us today. I understand this COVID, this is odd for everybody, this COVID environment, and I hope that you're all doing well, managing to move forward and haven't experienced very bad experiences. And I mean, I even have friends that have had some close calls with this. So again, the best to you all in these times. But this puts us in a position where we're talking to a camera instead of you directly. We're all on our side very uncomfortable with that, right? We're used to knowing your process, understanding what you need, and then talking to you directly about your specific problem. So this thing about talking to the camera just is we're certainly not professionals, and we are gonna miss something that's important, I'm sure. So if you could do us a favor and use that chat feature, keep us honest here, ask us questions, and kind of keep us focused on what your specific issue is, that would be great. Otherwise, I'm going to introduce Jeff here in a few minutes. We have a great story to talk about solids thickening. Jeff is the vice president of sales, and he will lead this presentation after that. And we're trying to keep kind of a dialogue going back and forth, so it's not quite so dry for you, the viewers. All right, Jeff.
Thank you, John. Thank you, Andrea. So our topic this morning is breaking the paradigm of solids thickening in industrial settings. And we're going to talk about, I think first what might be prudent is to talk about solids in general. What is that paradigm of solids thickening? John, I'll ask you, what is the paradigm of solids thickening?
Well, I think that there's a lot of issues with getting very high solids. Biomass is kind of a difficult thing to treat in high concentrations, and a lot of the digesters and the WAS waste streams get up there in fairly high concentrations, and you're sort of limited by this especially in flotation, by something we call solids flux. And I believe that we've kind of destroyed that. I mean, we have several examples now of very high solids flux numbers, very low chemical consumption to achieve very good results, to where, the clarifier may not be a very good option going forward compared to what we could do. So.
Yeah, so I think, and we should probably define, we actually thicken in several places in an industrial plant. And what's often typical is, first you've got primary solids, which are the TSS and potentially FOG coming out of a plant that it is the first thing that's generally done with filtration or what we'd call pre-treatment. And that's typically where flotation is applied, where you're clarifying the water prior to it being discharged either to a POTW or a secondary treatment process that the plant may have. So the solids that are coming off of that flotation vessel still have to be disposed of or rendered, and they generally, sometimes that's done on site, sometimes there's rendering on site, but most often they're trucked down the road. And of course, the more water you have in those solids, the more solids you have to truck, the more water you're trucking down the road. So obviously that translates to cost. And I think there's a lot of focus put on in industry about how do we handle those DAF solids. It's rare when you go to a conference at least in the protein world, that somebody doesn't bring that up. What do we do with these DAF solids? So thickening, of course, is one of those steps to minimize the amount that you're dealing with. And then, of course, if there is secondary treatment going on, then you've got to take care of the biological solids, whether that be aerobic or anaerobic generated biosolids. They still got to go someplace. Most often they're being land applied, but of course, if we can thicken those, that's the less we have, the less it costs to perform that. So let's talk about thickening. And I think one other thing that we should talk about is what's the difference between thickening, dewatering, and drying, because those are three different things that happens to reduce those solids potentially. Thickening, of course, would be what we're involved with, and there's other types of devices out there that can thicken solids, whether that be gravity decant, gravity belt thickeners, rotary drum thickeners. And am I leaving any out, John? Anything else you've seen?
Oh, off the top of my head, but I think we got the idea, Jeff. Yeah, I don't have, I can't think of anything off the top of my head right now that would replace, DAF, D-A-F-T, S-A-F-T, right? Right. Obviously the topic of the conversation, right? So, yeah. So.
Then of course, dewatering would be defined as further removal of water, which is typically presses, screw presses, belt presses, chamber presses, the old plate and frame type presses, as well as, of course, centrifuges, which is the world I came from. I was involved with several centrifuge companies for a number of years, and in fact, that's where I first became acquainted with SAF, and I'll get into that more here in a little bit. And then there's another potential step called drying. And we're seeing that in a few plants, both in municipal and industrial, but not employed that much in most of those applications. But anyway, so let's move to SAF. And I've got some slides to show you. When you can see these.
We can see them.
Okay, so this jar test, let's see if I can get this going. Whoops. Let me back up. I want to set this up. I want to preface this with an explanation. When I first became acquainted with heron, that actually came through a chance meeting. As I said, I was in the centrifuge world. I had worked with the ethanol industry quite a bit on dewatering what's called whole stillage, making it thin stillage. And then I transitioned to focusing more on food applications, where in fact DAFs, or dissolved air flotation, is used to do that clarification step, and we are getting some thickening with that as well. And so I was looking how to better break that emulsion with a centrifuge, how to spin those solids and get better fractionation of those solids. In other words, break that emulsion and a lot of what's causing that emulsion is the chemistry that's used to condition the water upstream, whether that be coagulants, polymer, whatever. So anyway, I'm thinking, I'm starting to say, as I was walking this trade show in Atlanta a few years back, I ran across a chemistry vendor, and I was talking to him about what I was trying to accomplish, and he mentioned to me, he says, you might want to check out SAF. And I had never heard of SAF, but he gave me John's phone number. I gave him a call. We started talking, and I thought, this is something worth checking out. In fact, I told a few of my clients about it. One of those was in Arkansas. It was a poultry company in Arkansas. And I invited John down to meet with them, and he and I went around with the client and grabbed water out of a number of their plants, several different spots in each one of those plants. And so what you're looking at here is a jar of pretty nasty water that came out of a wet well that had sat for a couple of days. This water stunk. It had gone septic. And so what you see is a little bit of coagulant and a very small amount of polymer that was put in to create a pin fly. And this is a tube coming from John's lab unit, his SAF generator lab unit. And I'm going to start this video. So what's happening here is a charged microbubble froth is being injected. And what you'll see is those solids actually appear to be growing in size as the bubbles attach to them. And what we witnessed was a very a very high capture rate of solids, very fast rise rate, and a very stable float. In fact, the environmental manager from the plant was standing next to me, and he said something like, "Wow, that was really something." And that, of course, piqued our interest even further, and we started checking out this SAF technology. This was all several years before I went to work for Heron. And we went to 3 different plants in 3 different states. And in fact, that company now in Arkansas has 9 SAF systems installed throughout their facilities. Some of those were DAF conversions, where the DAF was converted to SAF. We're going to be talking about that more here in the coming slides. But the also a number of those were new installations too. So let's talk about how SAF works. So what's typical, and I'm going to start off first by defining how dissolved air flotation works, because a lot of times people look at this, they're familiar with dissolved air flotation, and they think SAF is similar to that. It's similar to the extent that it is flotation. We're going to float those solids and skim them off with a rake of some type of tank. But that's really where the similarities stop, because the way that is formed, it's really quite a different process. So the way that a DAF typically works is you've got influent coming into this vessel, and you're grabbing water from the underflow or the lower portion of the tank where the water is theoretically cleaner, and that's being recirculated back into that tank with a recirculation pump that's pushing against back pressure. Compressed air is injected, and of course under pressure air dissolves in water up to a point of saturation. And then when that recirc stream re-enters the float cell, now you're at a lower pressure. So you've exceeded that saturation point, and so the air is going to come back out of solution. So in other words, it's going to form little bitty soda pop bubbles that work to float the solids to the surface and keep them suspended on the surface long enough to be raked off and disposed of. And of course, the clean effluent is going out this way. So that's DAF. That technology has been around for 100 years. And there's different designs of this depending on the manufacturer of this system. Some sparge in air, some are creating bubbles with cavitation, and there's different ways to accomplish this, but there's really nothing special about those bubbles. So let's contrast that with SAF. So instead of a dissolved air system, what SAF does is create a charged microbubble froth with a froth generator. And that froth is going to be 40% air by volume. Compared to DAF, where that volume is more like 2 to 4% air as far as the saturation point of how much air you can squeeze into that water, this is going to have 40% air. And this is made at atmospheric pressure. There's no dissolving of air in the water at all. And that's going to be injected, if I get my computer to go here, let me back up a slide. And maybe there's just a lag because I'm in Kentucky and this is operating in California. But so hopefully you see a slide right now with a diagram.
You do.
Oh, thank you. So compared to DAF, instead of this, we've got a froth generator that's generating this froth that's going to be injected right here, and it's going to be stirred in very gently just ahead of the float cell. In fact, no more air is going to be injected into the float cell at all. Often DAFs continue to feed air in to keep that solids blanket suspended, but SAF does not require that. So there's going to be an air to particle reaction that takes place right here, and so that froth is injected, influence coming in here, froth is injected at this point, goes up, and these paddles are stirring that in to get that air, or to mix those bubbles in with that influent and get a good mix so we can get that air to particle reaction before it goes into the float cell. So I started to say earlier, these bubbles are much different than DAF bubbles. I'm going to ask John to tell us how they're different. Go ahead, John.
Yeah, thanks, Jeff. So these bubbles are generated, the bubble's actually an Afron, it was patented in the 70s, right? And the four inventors actually never figured out how to scale it and get it out of the lab. That's what we brought to the table in the mid-90s. So we were able to scale this and deliver pretty much as much air as you want to any process in these Afrons. And these Afrons are double-walled bubbles that are running about 7 to 25 microns in diameter. But they have some huge advantages to DAF bubbles, and one of them is that the wall on the bubble is a surfactant sheath, which helps you overcome the surface tension of the particle. And so we are received well by a particle. We get a lot of air on a particle just because of that. And then we also have an electrostatic attraction piece of it that actually allows us to act a little bit like a coagulant even in solution. Well, that gives us about 1,000 times the affinity for a particle in solution compared to a DAF bubble. And so our air is used very well. And because of it's unlike a DAF bubble, which is the particle almost resists, we are easily incorporated in the particle. And so we don't need as much air in an air to solids ratio basis because of that. Then the last thing is that, well, it's not the last thing, but I just lost my train of thought, but I'm going to go with the coagulant for these right now. So the little bit of charge in the small size of the bubble allows you to offset a lot because it acts a little bit like a coagulant. Like you saw Jeff's diagram of how it puffed up, right? It actually reduces the chemical demand quite a bit. And that then now came back to mind. The last thing is it doesn't coalesce readily like a DAF air bubble. It takes minutes to break down. And so with that, our air can be used. If it didn't get into a particle on the first pass, it has time to kind of be reincorporated. It's actually in solution for a couple of minutes, right? All right, Jeff.
Yeah, thank you, John. So as John was explaining, these bubbles act a lot different. So they're going to attach to the solids before they go into the flotation cell, and then no more air is going to be put in. So it just creates all kinds of benefits. We're getting higher capture rate, quicker flotation, allows us to get by with a much smaller footprint, and as I said earlier, it creates a very stable float. And that stable float really helps in both primary and secondary solids thickening applications, because really all we're doing is the longer this can sit up here and float, the quicker it's going to the more we can dewater. And in fact, John, anything else you want to say about those solids sitting up top? Why do they dewater better than typical?
Well, we do get a lot more air in there. We get much faster rise rates. Right? You don't see anything like a rag layer in our solids. And so with all that air, the solids sit clearly above there's a clean break between solids and water, and the solids sit above that break. And so and they'll stack inches thick. So it actually can dewater better. It just drains through the solids better.
I'm trying to get my computer to work again here.
Okay.
So, sorry about that. Still a lag time, I think. All right, so we've had some diagrams, and let's talk about what the actual equipment looks like. Of course, this is a pretty big unit, isn't it, John? That in terms of SAF, this has got quite a bit of flow capability.
Yeah, it's probably third from our largest unit right here, right? So we have two units that are larger than this. But on I think I'm going to just go through this diagram, kind of tell you what's what up there. On the top left, you'll see, and again, I'm looking over the top of a camera to a diagram I have on the wall here. But on the top left here, you can see the flock mixer that Jeff was describing earlier. You can see the gearbox there, and that gearbox, of course, is driven by a VFD. The water comes in. You can see the pipe coming in. The water comes in, gets diverted into two nozzles going into the clear floater. Just before it hits that T, right in the middle of the mixer, all the froth is fed right there. So, and then on the right side is what generates the froth. That's our secret sauce, right? And so that generates a foam, a micro froth foam that we deliver to the process. All the processes contain to maintain the proper surfactant concentrations, the proper water levels are all automated. And go off of a flow meter or a float switch. So the reality is, if you need to add, if you're within the spec of the equipment, to add more or less air is about opening and closing a diaphragm valve. Not too different than just a water faucet, right? And you can add more air or less air. So in certain applications, that's very useful. But everything else will adjust upstream of that. And then on the bottom is a flock tube, kind of a traditional plug flow flock tube. Again, if you're just adding polymer, we're probably not using much of that tube. Maybe the last 10 feet or so, where we'll feed polymer in 1 or 2 locations before the frothing agent's injected and it goes into the mixer. So that actually for us becomes more about providing residence time for coagulation and pH control should you need it. And then on the right side, you have a CF1000 float cell, and that float cell, is good for about 2,800 gallons a minute of several thousand parts per million water. It's a cross-flow float cell, so all the water is introduced in the length on one side and retrieved in a weir on the bottom of the far side. And the weir is the entire length of the float cell, so you have it doesn't look as good oftentimes to the eye because you can see, in this case, 20 feet of weir. But as the water, if you have varying water flows to some degree, it doesn't create a need to adjust the weir to accommodate at least modest changes in water flow. In addition, the skimmer, of course, goes along the length. The skimmer has an on-off delay timer for allowing the solids to sit up on top and drain water, and then also there's a VFD to adjust the rake speed. We also, in later models, this one included that you're looking at, we have a longer beach to provide for once the solids are dragged out of the bathtub, we call it, and it's on the beach, it sits on the beach longer so we can even further dewater it to the point where we can easily get too thick of solids, and I'll let Jeff take it from there because there's a downstream dewatering tank here. He's going to talk a little bit about that right now.
Yeah, in fact, just walk through that real quick. I think it was probably apparent, but just to review. So water's coming in, it's being pumped through the serpentine, and this is used to, take coagulants upstream. Polymers coming in, being injected into one or more of these elbows. And so you've got a flock solid, water's coming this direction, which in this installation is coming this way, comes down here, froth is injected here, it's being mixed here, and then it goes in the side of the flotation cell and comes out the other side treated. And then of course the solids are going up, there's a rake, and it's being conveyed up a beach where it's separated from the water, and of course those solids fall by gravity. And this particular company actually, and this is Simmons Poultry, where this was taken in Gentry, Arkansas. This is they've learned that they can put in a secondary decant tank to get even drier solids. And something they've noticed, and we've noticed in many of our installations, that these solids tend to float a second time. It's such a stable float that it can be agitated and they'll float again. So they'll have a ball valve on the bottom of this that they'll either leave cracked open or come by maybe once a shift, crack it open, and let these solids build up to further drain. And then, of course, here's a solids pump that pumps it off to wherever it's going. I think they're land applying their solids. But I do recall when this was started up last fall that the environmental manager called us and he was laughing, and he said, we got those solids so thick that they were stacking up over here. They wouldn't even flow over to the pump. So they had to back off on how much they dewatered. And those primary solids, they're hitting in the 20 percentile range. Of course, a lot of that is fat, so that's still a liquid, but that's a number that you would normally hear coming off of a press. And so I'm not going to say that we can get as dry a solids as what you would a belt press or a screw press, but it's a much more thickened solid than what's typical for DAF.
And you know, might be worthwhile pointing out is you might be able to avoid downstream dewatering equipment with this.
That's a good point. Or that equipment could be smaller.
Exactly.
It's going to take the load off of that equipment, which typically it involves polymer, which is more expense. So the more we can thicken that, the less polymer that needs to be used downstream.
Exactly.
So before we get into this, and we're going to talk a bit about converting DAFs to SAF, which that's, as I said earlier, that's probably more than half of our business. We've got a video of this particular client that, let me just preface by saying that one of the gentlemen, it's been a little while since I've seen this video, but I do know one of the gentlemen, he was working with us when he was involved just with wastewater. He's now moved up to being chief engineer for the company, but he'll be talking a bit about his experience with SAF. So if you can play the video.
I'm Seth Walters. I'm the environmental director for Simmons Foods. I am in charge of environmental operations and compliance. We met Heron about 3 years ago, and we started to learn about the SAF technology. Some of the claims that they were making were new to us. We didn't fully understand the technology at the time, and we thought that based on previous operation experience, some of those things might be hard to achieve. But we've since learned that they're capable of that. We have also retrofitted SAFs that were previously DAFs. And what we saw is the design throughput went from 1,200 gallons a minute to over 2,000 gallons a minute. Similarly, we have another DAF in Southwest City that was also retrofitted. And in that scenario, we were actually floating biological solids, and we were limited on the amount of solids we could float per square foot of the DAF. And once we converted that over to a SAF, we were actually able to achieve somewhere along the lines of 200 or 300% more solids floated per square foot, which allowed us to put more water through the system. So at both ends of the system, our primary solids removal and our biological solids removal, we were able to use SAF technology to increase our design throughput while increasing our water quality coming out of the equipment.
Enough that we bought these two new ones. We then converted two existing dissolved air flotation units to SAF units. They're all working fine, and because of that, we purchased two new 2,000 gallon a minute units for a new facility we're building. We just received a small 50 gallon a minute unit for a plant we have in Milan. So the fact that we keep buying them means that we do think that they do the job.
My name's Kashua Thor, and I'm the environmental process engineer for Simmons Foods. My job is to assist and oversee environmental compliance and regulations. As the company is growing and demands are increasing, SAFs have been able to be 6 times more efficient than the previous processes. We've been able to use our existing equipment to convert to the SAF to meet production limits, and we've also been able to save chemicals used. So with the polymers that's used for wastewater, we've been able to reduce that as well as remove other components of wastewater such as phosphorus.
Oh, we're done with the presentation. I'm sorry. I did not know we were done with the presentation. I thought they were going to talk a little bit about that video. Again, I apologize. We are all very new to this. Let's go to questions and answers, shall
Very
we?
good. Okay.
So it looks like, I'm sorry, Jeff.
Yeah, sorry, I've got more to say.
Oh, see? I knew it wasn't me.
All right, Jeff.
So,
Why don't you go ahead? I'm sorry. For those viewers out there, we apologize. We tried to fit in another video and it got us off our game here. So, all right, Jeff, go ahead.
yeah, you bet. Can we put our slides back up on the screen? Let me know when you can see them.
You're
They're
good.
there. We got them.
You bet. So we talked about converting DAFs to SAF, and there's actually two of them in this particular plan, which is in Southwest City, Missouri. And this is and I think Seth probably talked about that some in the video that you saw. But I'm sorry, I couldn't see that on my end. What's playing for everyone else is not playing in Kentucky right now. So anyway, what we see here is a DAF, a pretty good sized DAF that's used on secondary biosolids. And to convert that to SAF is really just two components. We've got our froth generator and we've got the mixer that we talked about earlier. The serpentine was here already, and of course the flotation cell was there already. So what we do is we custom build these mixtures to fit the application so the flange is made up. And then of course the froth is being generated with this mixer, and it's going up this line right here and injected here, and then being stirred in. And of course there's a shaft with paddles welded to it. It's being stirred as it goes in, and then it takes a right-hand turn, goes into the float cell. And of course the environmental manager of the plant is standing right here. Let me get to the next slide. In fact, this slide right here shows what the inside of that mixer looks like. So again, influence coming in here, froth injected here, stirred in just before it goes into the float cell. And so thickened solids, and I know this plant's hitting somewhere around 5%. They increased their flow capacity by well over twice as much capacity, as well as solids loading. In fact, one of our other presentations we did for WebTech, we got into this in some depth, what they saw as far as cleaner water coming out the back end. Higher performance, a whole lot of savings in chemistry and energy, to the tune of the system, the conversion paid for itself in much less than 6 months. It's probably less than 4 months. And then I know they said they're hitting somewhere around 5% solids, which Andy, the environmental manager, said, that's just a function of what the company that takes the solids away. That's what the limiting factor is. They don't want the solids any thicker than 5. So aerobic solids, John, what have you seen us do? What have you seen us being able to hit?
I think hi Jeff, thank you. I think the highest number we've seen come out of aerobic solids applications are 10%. I think 4 to 6 comes with no polymer or just little polymer. 6 to 8 is, you're actually trying to dry the solids, and you're going to add a little bit more polymer. You're going to spend some more time dewatering. And 8 to 10 is maybe a function of the status of the aerobic solids themselves, whether there's been some level of digestion going on or so. But we've seen numbers on occasion as high as 10.
Yeah, so in fact, I know, John, you and I just had a conversation this morning about this, that of course we can take out the water that, biosolids are cells, they're microbes.
Exactly.
And there is water trapped within those cells. So we can remove the water that's on the outside of, in between those cells. And I think, maybe we talked about this a little bit already, but the longer that this sits on the surface, and because we've got such a stable float, the more that water can drain out.
Exactly.
I'm trying to advance the slide, but again, technical. So, this is one of the facilities that, I'm jumping around. I apologize. This is one of the facilities that Andy and I visited. In fact, that's him again up on the catwalk. John, talk about this one a little bit. What's this one doing?
Well, so that was treating, for the most part, anaerobic solids coming at us. It's been a while, so I guess I'm not sure of the concentration coming at us. But we were removing. They were having trouble achieving with other technologies, 70% removal efficiency, which was creating a lot of solids cycling back into the process that they couldn't get rid of readily. And so, why we were selected for that application, besides being very competitive in price, was we were achieving for the years that was running out there, we were achieving 98+% removal. And the thickened solids were above 10%, and they were able to go to a fan press and achieve like 20% solids. So that was a very successful trial for us. Not a trial, that was actually an installation for us. It's been maybe that went in about 2015, something like that.
Yeah, John, this was actually presented, this case study was presented at WebTech a couple of years ago.
It was. It was.
And I do recall that it was in that case study, which is available on our website, by the way. It mentioned that the amount of polymer consumption was much less with higher removal than what was seen with any DAF and any of their other plants.
Yeah, so, readily the plant managers out there would tell you that it was by far the best performing DAF in North America. So it not only achieved those numbers that we achieved consistently with less polymer, but the solids were drier, right? So they had, right around 10% solids going to a fan press. That just made even downstream chemistry less. So, and the material released from the fan press, so fan press worked remarkably well. They do, as long as you're not looking for 25% solids out of them. But so we went to a fan press and it worked well, and the whole system worked very well while they needed it. So.
Yeah, and I think another thing that impressed us when we first saw this was this unit will do 1 million gallons a day, 700 GPM. And
So that,
with the DAF, you would expect to see a much larger unit.
yeah, so that skid itself is 28 feet long, about 10 feet wide, and the float cell itself is probably 35, is right at 35 square feet of float area. And so, and we could run that at at 1 million gallons a day, 700 gallons a minute. For fairly, thousands of parts per million solids. We have competition out there that they'll tell us they can get 20 gallons a minute per square foot, but that's oftentimes in things like drinking water, right? Where you got almost no loading. But we load these things up. We can load these cells up to 45 pounds per hour per square foot, and oftentimes that is at 20 gallons a minute per 20 gallons a minute per at a hydraulic loading of 20 gallons a minute per square foot. So
Right.
it's pretty unique in the industry.
Yeah, so in fact, let's talk about another trial that you and I were both recently involved in up in Minnesota. And I'm hoping the slide is advancing. I'm clicking the button. So here we go. Can you guys see this?
I can, sure. Yeah.
On the screen. So, and this is obviously taken from both sides of the trailer. Just to explain what we've got on this trailer. This is one of two trailers that we've currently got. So we've got polymer dilution here. There's a serpentine that you can see from both sides here where we can inject in polymer at multiple points. Of course, the control panels down here on the end. This is the flotation cell. This is what we call our model CF125, which has 17.5 square footage of flotation area. Here's the mixer, and this is the froth generator right here. So water's coming in, it's going through this, polymer's injected, and then it actually drops below the bed of the trailer, comes back up into the mixer where the froth is injected right here. You can see the line. Froth's injected, stirred in, and then it enters the flotation cell. Solids are raked off here, go this way to the solids pump, which you can see again right here. I'm hoping you can see my cursor moving around.
Yes, we can.
And then of course the clean water is coming out in the water launderer right here and being drained off. So this particular trial, this was on anaerobic biosolids. And this was coming at us at a rate of around 5,800 ppm of TSS. And so I think I've got some videos of this. Yeah, so here we go. This is, that was the water coming in. Here's the water going out. So I wish I had a shot of what this water looked like coming in, because it was very dark. And, you know, it was 5,800 is pretty heavy loading. And so let me see if I can start that again. Oh, here we go. And again, I do apologize for the delay in the computer. Is that starting up? There we go. That's what we wanted to see. Is you can see how thick the solids are getting. And of course the rake's not running right now. It was on a timer. And then this is the beach end. John, you want to describe what else we're seeing right here?
Well, the solids are accumulating. I mean, there's probably a 6-8 inch bed of solids that are accumulating on there, and they're dewatering. They're draining the best they can. In fact, if you saw earlier in the video, some of that water is just being captured on the top. Here you go, the skimmer is just starting now. So you can see how it's breaking off. It's fairly thick solids. At some point, people don't want it any thicker because they have trouble pumping it to its final destination. But this is I think it's right around 5% solids. And you know, we could have left it up there longer. We could have added a little bit more polymer and got it even drier. And you can see how thick a bed that is. So, you know, I think during this trial we were averaging 30 pounds per hour per square foot. I know, Jeff, that when you were playing with it there toward the end of your stay, after I had left, you got it up to about 45, 46 pounds per hour per square foot. We have additional data from other sites where people have loaded them at really high solids flux rates. So, and this is all at modest polymer consumption rates. Oftentimes half the DAF or a third the DAF would use to do the same thing. So the surfactant coated Afron is particularly good at engaging these particles and floating them.
Yeah, so the solids flux, the amount of solids that we can handle per square foot, that was on this particular project, that was a big part of this on when you look at the capital costs, 20-year operating costs. Of course, capital is the upfront part of that. And not only were we somewhere around a half to a third of the physical footprint, and this was a pretty large application, I think full scale about 2,800 gallons per minute. So pretty good size system that's going to be going in. But not only is our system 2 or 3 times smaller, but the building it has to go in is also 2 or 3 times smaller. So considerably less capital expense, but ironically, the decision to go with SAF wasn't based on capital at all. In fact, I don't think our competitor even, I maybe didn't mention, right next to our trailer was a competitive DAF being trialed in parallel to us at the same time. And I don't think they even provided, the engineering firm said they never got a quote for the capital after this trial. So the decision was made simply on operating expense, solely on how much polymer the system was going to use, what we proved we could use. And that was somewhere around 25, I think maybe to 40% less polymer, and which worked out to more than $250,000 a year. So over 20 years, that's a lot of money. And then of course the other thing was just how easy it was to use. And John, I know I'll let you talk about that a little bit.
Well, I just remember the quote from when it was being presented to the board is that the operator said, not only did we achieve all these great results with such little amount of polymer, but this was, quote, stupid easy to run. And so when they were operating this, of course, we were, we actually left maybe a week before the trial was over, and the operators and the engineering firm actually ran the trailer. And, you know, they were playing with it. They were trying to reduce, you know, challenge the polymer numbers we'd given them and try to get, you know, particularly low polymer. They disrupt the process. They turn it back up. They says within a few minutes it was back, or they let the solids build up way too high on the float cell, and then have the skimmer come on later and for a little, you know, trying to further dewater the solids on occasion. Turns out moving the solids was the issue after that. But the you know, but at some point, like anything else, you start getting a foot, 2 feet of solids, it's going to start washing over. And then of course they said we just turned the skimmer on, boom, it came right back. So it's pretty simple process to operate. We design it that way. Our efforts to continuous improvement always incorporate that. Is how do we make this easier to run for someone that doesn't know it like we do? So the you know, we warranty the physical can for life, but the rest of the stuff is pretty much OEM available parts that can be swapped out. I mean, the maintenance on it's very low. I mean, and how you saw those slides on Anheuser-Busch, they used to tell our customers who used to bring by there, he goes, you know, in 2 years, all I've done is grease these zerts. I haven't done any maintenance on it at all. So taking down the tank occasionally to hose it out, maybe every 6 months, depending on how well you know, how much solid settles, you can take it down once a quarter, once every 6 months, hose out the float cell. We do have bottom solids collection for that, but we don't oftentimes put them in. We're kind of running a little low on time, so we leave some time for question and answer. I'm going to say,
Exactly. So Andrew, why don't I kick this back to you? Have we had any questions come in?
We actually have had a couple questions come in. Thank you. First one is, why do your solids release water easily, or do they?
So release water might not be an accurate statement on that. The solids release from dewatering fabrics easily, which makes them more easy to dewater. And they drain solids very easily, and that has to do with the gelatin type float and how buoyant the solids are and how well they sit up above the water so they can drain. And the fact that they're so robust that we can leave them there for quite a while without running the skimmer, so they can continue to dewater.
Okay, great. And next is, what are the highest percentage of solids you have seen from this equipment?
I would say, Jeff, you may be able to help me out on this, but I'm thinking poultry, primary poultry, we get probably the highest solids. And I've seen I've seen a few numbers that run in the 35, 36% range. I think typically in poultry we are in the high 20s. And when you look at biosolids, you're kind of looking at about, you know, anaerobic biosolids, I think we've seen a high of 10, 11, 12. Aerobic biosolids, I think we see a high of about 8 to 10. I've already talked about kind of the ranges we see in the aerobic side. You have anything to add to that, Jeff?
Just on the primary solids, it's going to all be dependent on where those solids are coming from, what type of plant it is. You know, obviously solids that don't absorb water, those are easy to dewater. You know, a certain amount of water is going to be trapped within the solid itself. Just the same as with biosolids, you've got a certain amount of water trapped within the cell membranes. So it all depends on what type of solid that it is. But yeah, the numbers that John was throwing out there, pretty much the same thing I've seen.
Okay.
Great. We do have a third question. It is, can the maintenance for the froth generator be done by the user and or operator, or does a Heron representative have to go there to do the maintenance?
It is very, well, there isn't much maintenance. Maybe I should start. There's very little or no maintenance on the generator. And the problems typically are the metering pump, which is kind of an Achilles heel of just about every system, right? And then there's this water solenoid. And I would say that those are the two things that for the larger units require some attention occasionally. And certainly most of the time your plant operators can do those maintenance. Occasionally if a pump goes out, it needs to be swapped. But all this equipment, aside from that, we call it a sealed generator module or the can, which is that can's guaranteed for life, but everything else is OEM and should be off the shelf available. And you know, if you have a mechanic on site that does other maintenance, certainly well within his capability to address almost all the issues with the site. I'm going to say all the issues associated with that generator. Did I answer that question? We've got a big delay, but let's move on for now. Let me know if you need some more clarity, whoever asked that. Yeah.
Perfect,
Okay,
thank you. Okay, well, in the meantime, that's all of our questions for now. I do want to encourage you guys, if you want to learn more, please visit our website at www.heroninnovators.com. You can reach out to us anytime at info@heroninnovators.com and email us or give us a call. All of our information's on our website, but we would love to talk to you more about SAF if you have any other questions. Until then, I'm Andrea Hofstetter. This is John and Jeff. Thank you for joining us, and everybody have a wonderful Wednesday. Thank you.
Thank you, everybody.